Let's review the strong acids, strong bases, and some options for weak acids and weak bases. So, to begin with, what is a strong acid and what is a strong base? These are substances that will dissociate either completely or nearly completely in solution. Um, that is, they're very strong ions. And let's start with the strong acids. We have hydrochloric acid, or HCl, hydrobromic acid, HBr, hydroiodic acid, HI. That's simply the halogens without fluorine. You might ask why fluorine isn't on there, and it really depends. In water, it's not a particularly strong acid, but in other circumstances, you can make it a very strong acid. But since we generally deal with aqueous solutions, it's not included. The bond between the hydrogen and the fluorine is just quite strong, so it doesn't completely dissociate. And then we have a selection of the oxo acids, so called because they have a lot of oxygen associated with them. We have nitric acid, sulfuric acid, which is diprotic, has 2 protons that could come off, and perchloric acid. Now, out of all of these up here, perchloric acid is the strongest, closely followed by sulfuric acid. Perchloric acid is not only a very strong acid, it also has a lot of oxygen on it, so it is very reactive towards organic material. Now, let's look at our strong bases. We begin with lithium hydroxide. It's not quite as strong as the others, but it is quite strong. Then we have sodium hydroxide, which is, I would say, the most common one in use. Potassium hydroxide, rubidium hydroxide, and cesium hydroxide. Now you'll notice that's essentially just the alkali metals, the first column of the periodic table. And that's exactly right. The other calcium hydroxide, barium, strontium hydroxide, those do not completely dissociate at higher concentrations, whereas these bases will dissociate up to quite high concentrations, and so that's why these are really the list of strong bases. Now, you might be asking, why are we going over the list of strong acids and strong bases? Well, the reason for that is they're very small lists. They're very short. And so it's possible to learn all of the strong acids and all of the strong bases that we would encounter. Conversely, there are thousands upon thousands of weak acids and weak bases. Just way too many to learn them all. And so, as long as we know which ones are strong and we're capable of identifying what an acid is and what a base is, then we can use that information to say, oh, is it on the list of strong acids? It's not? Well, then it's probably a weak acid. Or same thing with bases. Now, I haven't included every single strong acid on here or every strong base. There are some a little bit more specialized ones that get used in more in organic chemistry or just to push the limits. Like, for example, here's one that is really strong. This one's a negative charge here, and then there's H plus. This is called fluoroantimonic acid. Some places also call it magic acid. This is a superacid. And you would make this by combining antimony pentafluoride with hydrofluoric acid, or HF. And when those two would combine, it would make this. The fluorine would then attach to the antimony, and that leaves the hydrogen very free and available to react with anything and everything. And this is extremely powerful. In fact, it's called a superacid for that reason. You just won't encounter this that much because it will dissolve glass, it will dissolve candles, concrete, asphalt, any of those things it can go through. So, if you ever see a substance in a cartoon and it's dissolving everything, maybe it's this. There are also some super bases out there that would be extremely strong. Some of them are very strong, but just not very quick to react. And so those are called like proton sponges or other things where they'll grab onto a proton, not let it go, but they're not particularly fast at it. Some of those examples would be DBU, which I forget how the structure is, but it's there's the abbreviation. It's an organic base. It's not particularly fast at its work. Like these are quite fast, but it's very strong. But that's not our focus. Now let's also look at some typical weak acids and weak bases. One of the common structures for weak acid is a carboxylic acid, which has this carbon double bonded to oxygen and then another bond to an OH here. And it's this proton right here that is acidic. This one can come off. Now this R group over here is just whatever we want it to be. It could be other carbon stuff, it could be a ring, it could be a halogen, could be hydrogen. If it was hydrogen, it would be called formic acid. If there was a CH3 here, it'd be acetic acid. Benzene ring, benzoic acid. So there's a lot of variability that we can have that has this particular group on the end just by changing this group over here, this R group. Now, we can also have organic weak bases. And one of the common things to do is to use a nitrogen-based base, which is an amine. That's the name of the group. And we can have just one carbon-containing thing on the nitrogen. We could have two, which would look like this. Or we could have three carbon-containing things on there. All of these are bases. Now, they're actually Lewis bases because there's electron pairs here, and this electron pair can be donated away to an acid and react with it. So, this is just an idea of the strong acids, strong bases, weak acids, weak bases, and we're going to talk more on what makes an acid strong or weak and how electrons actually play a role in that.